name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunication Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing them. Welcome to the 15th in a series of talks in the High-TS RF Measurement Seminar Series. The talk today is Resolving RF Interference, RF Front-End Overload. Last week we talked about co-channel interference, and that is probably the more intuitively, easily understood of the interference mechanisms. And this, of course, is a case where a transmitter is operating at some frequency and it produces certain levels, typically of out-of-band or spurious emissions, and a receiver is running at some frequency over here that we'll call the receiver frequency, where this is the transmitter frequency. And these emissions on the receiver's desired operational frequency, in fact, cause the interference effect to the receiver. That's probably, I would guess, the type of physical phenomenon that most people envision when they think about RF interference. The problem that we're going to talk about today is not a result of any artifact of a transmitter's operation, other than the fact that the transmitter is running, but rather is an artifact of the design or lack of good design in the front end of a receiver. So the problem arises typically and almost always when, and I'll go to the design issue first and then come back to what happens, when someone builds a communication or a data transmission system which involves an antenna which goes into a low noise amplifier, and the low noise amplifier then goes into, at some point or another, typically one or more stages of down conversion, and then goes into the intermediate frequency stage and then produces some sort of output. Could be data, could be video, whatever. And we've talked in this series about how a good RF front-end design should ordinarily incorporate some kind of filter in front of the LNA, which is typically, but not always, a bandpass filter. A bandpass filter, of course, would have a frequency response characteristic that would look something like this in terms of throughput versus frequency. You could also, depending upon circumstances, build a filter into the front end which specifically eliminated some band like this, where it would eliminate energy in this band but would pass energy in this band. And of course the assumption is that our receiver is running in here. Or you could even imagine a front end where you're trying to get rid of energy from a specific transmitter that you know of that might cause some problem, and so you put a notch characteristic into this filter. But most commonly, in general, people will design this as a bandpass filter where the intention is to pass energy through the bandpass filter through the part of the spectrum or the entire spectrum band in which a radio is supposed to operate, and then eliminate energy outside that spectrum band. So here we have the receiver frequency maybe tuned here, or maybe here, but this filter sits here at the front end. Now, so that is a good way to design a front end. Problems with bandpass filters that cause people to sometimes not include them in an RF receiver design are oversight or lack of oversight, that is to say they basically neglect it, or cost. A bandpass filter, or any filter at a front end, does have some kind of financial cost typically associated with it. And a third reason is, and this is more of an engineering reason, is insertion loss. Inserting a filter at a front end can introduce a half dB, maybe 1 dB of insertion loss, and for some communication systems this could be considered to be a problem. So for at least any of these three reasons, bandpass filters are sometimes not incorporated into the front ends of radio receivers. Oh, and there is a fourth possible reason. Some radio receivers need to operate in multiple bands, or they need to operate over a range of frequencies such that it's impractical or otherwise difficult to get a bandpass filter which will adequately or properly work over that frequency range. We've seen that in the ITS measurement system, we use a bandpass filter at the front end, which at low frequencies is a varactor technology, and at higher frequencies is a yttrium iron garnet, a YIG technology, and those are tunable bandpass filters. They actually track our measured frequency, but again, they have insertion loss, and they are expensive. They also add to the complexity and the weight of a receiver system. So, suppose that we build this kind of receiver, and for whatever reason we leave out the bandpass filter, and we therefore have a system which in terms of its RF response looks like this. Here's frequency, and here is the RF response of the type of receiver that I've drawn. What controls the RF response of that system? There's no filter in front of the low noise amplifier, and we'll assume that the antenna has a wide operational frequency range. Well, it's the low noise amplifier. And we'll say that this is the receiver frequency that we're building the system to work at. And we will assume that when a person was designing the system and they said, okay, we need to design receivers that will work across some particular band of spectrum, that they had this in mind. They had it in mind, and I'm intentionally not drawing this symmetrically, they had it in mind that this would operate across this part of the spectrum. The receiver might be tuned here, the receiver might be tuned here. And so they said, we need to have a system with a low noise amplifier that is specified or spec'd to operate anywhere from F1 up to F2. Here's F2. And so they buy a low noise amplifier that's spec'd to work across that frequency range. And in fact, you'll get the low noise amplifier, it'll come in a package, greatly magnified here. This is probably only a couple inches across. And it'll have a spigot for input and a spigot for output. And right there on the package, it'll say, in some coded nomenclature usually, that it operates between F1 to F2. It'll also list the gain. It'll probably say, let's say 35 dB gain, and it'll say perhaps 3 dB for noise figure. Now again, these are actually usually listed in a specialized kind of cryptic code, but you look at this and you say, good, F1 to F2, 35 dB of gain, 3 dB noise figure, great. You go ahead and you insert that into the system. Now, the mental model that a person has typically developed at this point for this low noise amplifier is as follows. The person typically envisions the low noise amplifier as having a frequency response that looks something like this, where they're imagining that this represents 35 dB of RF gain with some fairly low noise figure across this range. In fact, we could plot noise figure down here in red, and they're envisioning that this has a noise figure down here of 3 dB, and we'll plot it like so in red for the 3 dB noise figure. That's what they imagine this amplifier is doing based on what's on the package. The reality is that in general, the amplifier has a frequency response that actually looks like this. I'll draw it in black. It does typically have this kind of response across its center frequency operating range, but then it goes way out across the spectrum like this before it rolls down, and comes way out like that before it rolls down. And you say, well, wait a minute, why does it have such a wide frequency response range? It said F1 to F2, maybe, for example, 3700 to 4000 megahertz on the package. The reason seems to be that manufacturers typically guarantee, the word is guarantee, they guarantee that it will produce those noise figure and gain responses across that range from F1 to F2. They didn't guarantee, they didn't claim that it didn't respond outside the frequency range. They assumed that what you asked for when you ordered it was a minimum specification, not the specification. So, for example, they could build an amplifier that operates all the way from 1 gigahertz at the low end to, we'll say, 8 at the high end, and that when you ordered one that was supposed to operate from 3.7 to 4.2, they basically took one of these 1 to 8 amplifiers off the shelf, checked it to make sure that it had the right gain response and noise figure across that particular frequency range, and that's the label that they put on the package. And if someone else buys an amplifier and they need the amplifier to work across this frequency range in here, then they'll take the same kind of amplifier off the shelf and put a label on that says, we'll say for the sake of argument, that says 2.5 to 3.0 gigahertz. Again, with whatever noise figure and gain that unit happens to have. And therein lies the origin, typically, of a front-end overload problem that is going to happen with some of these receivers down the road. Because, given that the unit, well, in fact, I'll redraw this. Given that the unit has a pretty good response well outside the band of interest, we'll imagine that this band right in here is some sort of communication band, and that this spectrum band down here, we'll say from here to here, is operated by some high power transmitter type system. For example, radars, maybe broadcasting. We haven't really seen much trouble with broadcasting, but it could happen, etc. Down in this part of the spectrum. Now, if this amplifier, which sees all of this spectrum at the front end of the receiver, is in fact subjected to energy with a sufficiently high power level in this part of the spectrum, and here I'll draw the spectrum of some sort of transmitter, like, for example, a radar that looks like this. And we'll imagine that these emissions, the unwanted and spurious emissions, out-of-band unwanted spurious emissions, drop way off from the system by the time it gets to this receiver band, so low that we can't measure them in that band, even if we get up close to the transmitter, which happens. But that it has a fairly high EIRP at its center frequency. We'll say maybe the EIRP peak EIRP might equal, for example, something on the order of a gigawatt. This power at this frequency, when it illuminates this antenna connected to this low noise amplifier, is going to feed into the low noise amplifier, and the result is that while that energy is going into the low noise amplifier, the low noise amplifier gain characteristic drops, and it doesn't just drop on this frequency where the high power transmitter is tuned. It drops, the response drops all the way across the operational response band of the low noise amplifier, and so its response ends up looking like this while it's being subjected to the energy from this transmitter. The transmitter hits it at a frequency completely outside the operational band that the people who built the receiver intended the amplifier to be used for, but the amplifier's response drops all the way across that operational band, and it can drop by 5 dB, 10 dB, 20 dB. We've looked at different amplifiers. We have an ongoing project in NTIA and here at ITS that's funded by the Office of Spectrum Management to examine these characteristics in more detail. But suffice to say that when the gain characteristic of this amplifier drops all the way across its operational frequency range, the result is that if this receiver was measuring a desired signal in this band, it will not be, well, measuring, it won't be picking up, it won't be properly processing, won't be able to process at all that desired signal as long as that interference is hitting this amplifier down at this frequency. And that is RF front-end overload. The reference to front end being that the low noise amplifier is at the front end of the receiver that we're considering. Now, for more information on this topic, I'll mention right now that we wrote a report on the subject in 1994, and you can look up additional information in this report, which is NTIA, I won't write the whole title, but it's NTIA Technical Report TR-94-313, and it is available on the ITS NTIA website, and it contains more information about the receiver responses and what happens to the amplifiers when they're hit by the high power signals. What I'd like to talk about today are methods for identifying this interference mechanism and then what you need to do to resolve the interference mechanism. The first clue that you might have that you have a problem with RF overload is when you've been informed that a receiver is having an interference problem and you've called the people who operate the receiver and you've talked to them on the phone, you've gotten information from them, and among the pieces of information that you got were the schematic block diagram for the receiver. And the first thing that we typically look for in a block diagram like that is in fact whether they do or do not show, back to the IF and then the output, whether they do or do not show any kind of filtering right there. It is possible that someone might have neglected to put a filter into the diagram if it exists, but if you don't see a filter there and people say that they're getting some kind of interference, you've got to immediately consider the possibility that they are in fact possibly experiencing some kind of RF front-end overload problem. Now in the lab session that we're going to do, we're going to look at a diagnostic procedure that you can operate right here at the IF to actually confirm or disprove the hypothesis that they're getting some kind of RF front-end overload. But I'm jumping ahead slightly. If in fact you see that there's no bandpass filter or any other kind of filtering here at the RF front end, and you go then, as we discussed in the last talk, to the site, you make measurements, you look at the interference in the system, you work your way through the possibility that there's no interference occurring, you discover that yes, there is a transmitter involved, and you identify what the transmitter is, all of which we discussed in the last talk. You'll recall that the next step in the process is in fact to look at the emission spectrum of that transmitter and measure it. If the transmitter is near the receiver, then you can go directly to the transmitter site, presumably from the receiver site, and make the spectrum measurement either with a truck or van vehicle like NTIA has or with a suitcase system. In other cases that we have encountered where an airborne system, which we'll draw looking like this, where an airborne system of some sort has been identified as causing the interference, you might need to actually find the airborne system, go to a location where you have these aircraft on the ground and have them turn on the transmitter, say it's a radar, from the aircraft on the ground. In any event, you need to measure the spectrum. And the reason that you need to measure the spectrum is because you need to know, and we'll say that this is what the spectrum looks like, you need to know the extent to which this transmitter is producing energy in the band of the receiver that would or would not be sufficient to cause co-channel interference. If you do see enough energy in the receiver band to cause co-channel interference, as we discussed in the last talk, then you're going to have to mitigate that in any event. Now, that doesn't necessarily mean that RF front-end overload couldn't occur, but if you see the in-band energy is high enough, then you'll have to mitigate that. And as we discussed last time, the way that you would mitigate that would be to install a filter on this transmitter, and the filter would actually knock down the transmitter energy in the receiver band enough to eliminate the co-channel interference. But suppose that when you do the measurement on this system, you discover that in fact the transmitter in question is simply not producing enough energy in the receiver band to cause the receiver to experience interference. For example, if the receiver has a noise level that we'll arbitrarily draw like this in decibels, here's the receiver noise floor, and you see this energy coming from this at a sufficiently low power that at the distance that this transmitter is located from the receiver, and given the receiver's antenna gain and the gain of the antenna on this transmitter, that in fact the noise from this thing would be 10 dB or more below the receiver's noise, then clearly this can't be causing the problem. And if this is a communication receiver, the issue is what the ratio is of the interference level from this transmitter in the band to the level of the desired signal that the receiver is working with. In that case, the receiver might be able to actually cope with some level of interfering energy that's somewhat above its noise floor, if that energy is in fact more than a certain number of dB below the level of the desired signal, and that'll depend on the characteristics of the receiver and what it's doing. In any event, if you determine that these levels are sufficiently low from this transmitter in the receiver band that co-channel interference can't be occurring, then barring case penetration, the only realistic way for this interference to be occurring is if in fact this thing is generating the front-end overload problem. And again, another clue is that this receiver presumably has no filter or has inadequate filtering at its front end. If this receiver does have adequate filtering at the front end and you're still seeing the front-end overload problem, now you've got a really exotic situation, which we did deal with and which I'll talk about in the next talk in this series. But we'll assume, first of all, that this is going to be a simple case, not a tricky case. If in fact you ascertain that this is what's happening and that RF front-end overload must be occurring in the receiver band, RF front-end overload must be occurring under this circumstance, then what's the fix? The only possible realistic fix is going to be to install some kind of filter on the RF front end. This is an example of a waveguide filter. We'll ignore the two parts that are in my hand. This is the actual filter. This is for a microwave system. It's specifically designed for digital point-to-point microwave links or for earth station links, and it consists of a piece of waveguide that goes at the front end. Interestingly enough, on this one, this is the filter, which is actually simply linked into a chunk of waveguide to make it mechanically compatible. But the point is that this is a bandpass filter which will pass energy in the receiver's desired band of operation and rejects energy to the tune of 60 or 70 dB or more outside the band of the receiver operation. You could use a notch filter to specifically reject one transmitter out of the band, but then you'd have trouble if anyone came up on a different frequency out of the band and could cause the overload problem. In any event, the key is that a filter needs to therefore be installed, if you're experiencing RF front-end overload, on the receiver, and nothing can be done to the transmitter to mitigate the problem other than turning the transmitter off. No spectrum mask, cleanup can be implemented, nothing, because of course again the problem isn't the energy that's in the receiver band. So we'll come back to that in the lab session. Any questions at this point about RF front-end overload? It's fairly straightforward once you know it and you want to look for it. Now, if we think that this problem is happening, and before we tell people who are operating a receiver
that they really have to get a filter, there is a test, a diagnostic, that we can do at the receiver site, and we can do this particular test whether or not we know anything about the transmitter involved, that's involved. And here's what we do. Given that we have in the receiver, I'll draw it like this time, here's our wide open LNA, some down conversion, here's the IF stage, and here's the receiver's output. What we need to do is in fact connect an instrument to some kind of output from the IF. It could be here, or it could be an auxiliary tap. An auxiliary tap that runs out, and we can either run it out to a spectrum analyzer, or we can run it into a detector. This is a discrete component detector. And then into an oscilloscope, like so. And in either case, coming out of these boxes, what we will do is generate a display, and we'll look at this in the lab session, and the display will be a time domain display in both cases. Bear in mind that the spectrum analyzer in a certain sense is like an oscilloscope that works at a slower time rate, and which has a detector built right into it. And we're going to look at the desired signal level coming out of the IF, which will look something like this. Here it is on either of these two units. It looks like this. Desired signal. And every so often, a front-end overload is occurring when this receiver is hit by the emission from the transmitter in question, which looks like that. We're going to see the following artifact show up. And the artifact is that after the pulsed emission from the high power out-of-band transmitter has occurred, the gain characteristic of the amplifier will have dropped, like I drew earlier, and we're going to see this happen, like so. We're going to see the apparent level of the desired signal drop below the level that we know the receiver's getting it at. Now what's happening is the desired signal's not dropping down. The response of the front-end amplifier is dropping down, and the result is that we see this dip occur as a result of the amplifier having been hit by this high-power pulse, and it takes some non-zero amount of time for the amplifier's gain characteristic to recover after it's been hit by the pulse. And the reason that the receiver is suffering degradation is the receiver's losing data while it's being hit by the pulse first of all, and while it's recovering. Because of course what's actually happened is when the pulse hit, the gain characteristic of the amplifier began to drop at that point. It dropped down like that, but we couldn't see it dropping because the pulse was coming through the system. But when the pulse ends, and we're considering here that this is radar pulse, but it could be from any transmitter causing overload, then what we see is just the response, the relaxation as the amplifier's operation comes back to life. And the reason I've drawn this is to demonstrate or draw schematically the fact that we can use a spectrum analyzer on the IF of the receiver, or we can use an oscilloscope. But if we see this kind of characteristic occurring, that's it. And what you may in fact see on a display if you go to a longer time base is first of all the characteristic of the receiver and the IF, and then if it's a short time base, you'll see a set of pulses, for example, coming in from whatever the source is, and then you'll see this happening right after. Whoops, didn't draw that too well on that one. There we go. See this happening after each one. That's it. That is our front-end overload. That amplifier is losing its gain characteristic at that point. So that is a check that you can do right at the receiver, assuming that you can get to its IF, and verify what's happening. Now, in a pathological case that I'll talk about next time, we saw that happening even though there was a bandpass filter at the front end of the receiver, and that's a different story. But it was, in a sense, front-end overload, even with a bandpass filter on. As I say, I'll talk about that more next time. So, having set all that, what I'd like to do in the lab session is actually generate RF front-end overload in a virtual earth station setup that we have, and then show how we actually see this happening. And so the system that we're going to be using is in fact a low noise amplifier with a little bit of extra circuitry that is built into a box, and this box has an output that we can in fact break out into either a spectrum analyzer or an oscilloscope. And coming into the LNA at the front end of our box, we have a signal generator that produces a desired signal, quote unquote, which in this case is just a carrier wave, but it could just as easily be a digital data signal of some sort. And coming in on a coupler into the same path, we have a high power, relatively high power, pulsed interferer down here. Draw it like this, like so. This is going to be running at a frequency of 3 gigahertz. The desired signal up here is going to be running at a frequency of 4 gigahertz. So there's going to be a full gigahertz, 1,000 megahertz of frequency separation between the desired signal and the high power pulse signal, and we're going to look at the output of this amplifier, which is in a virtual, but it is hardware, a virtual receiver that is representative of the RF front-end architecture of either a typical earth station downlink or a point-to-point microwave link. One final note. Historically, when analog signals were being transmitted into earth stations and point-to-point microwave links, front-end overload occurred fairly frequently, but people tended to ignore it because with an earth station downlink that would be downlinking, for example, a television broadcast picture, people just saw a screen picture that showed the desired picture information along with a number of little speckles that would pop up on the screen whenever the interference would occur, each of these speckles representing one of the pulses that were coming from the pulsed interferer. And I've actually watched this myself in a hotel room, and I timed it, and it was 4.75 seconds, and I knew that it was interference from an FAA air traffic control radar. Or in a point-to-point, I was really bored that night. Or in a point-to-point microwave link that was analog, people would be listening, and every 5 or 10 seconds they would hear a bzz, bzz, but they didn't care. Again, it was getting front-end overload, but with an analog system, people tend to look through it or hear through it, they didn't care. But as these systems have gone digital, they're able to do counts, measurements continuously of bit error rate, and the people who are operating these links suddenly see a bit error rate that jumps up every 5 or 10 seconds. They become concerned. It can also cause significant data dropouts depending upon how vulnerable the digital data protocol is to the interference, which, to sum it all up, makes the system more sensitive, not less sensitive, to the effects of the interference when it occurs. So we actually saw an increase in the number of reports and the complaints about the effects of RF front-end overload type interference back in the early 90s. That's why we wrote report 94-313 in 1994, because with the advent of the digital systems, this front-end overload problem suddenly came to the fore for earth stations and point-to-point microwave links. It can affect any radio receiver, but those were some of the prime examples. All right, so now we've seen what we're going to be doing for the lab, how we're going to have this set up. At this point, unless anyone has any particular questions, I'll segue into the lab portion. Okay, this is the lab portion of the talk. Here, we're going to replicate what we would see at an earth station or a digital point-to-point microwave link if we had hooked a spectrum analyzer and an oscilloscope up to the earth station. Typically, we would hook up one or the other at a time, up to the IF output or to an auxiliary output on the IF output. First, I'm going to look at the spectrum analyzer output. This is a typical configuration that we might use for spectrum analyzer. We go to 1 megahertz bandwidth. We could go to a wider bandwidth if we wanted to. And here we're just seeing the spectrum analyzer noise. And we are tuned to 4 gigahertz, which is the RF frequency. On a typical earth station or digital point-to-point microwave link, we would actually be tuned down to the IF frequency, but it would still look like this. It would have just gone through a mixer and therefore would be running down at 21.4 megahertz or something like that. But you'd see the same kind of display. Now, we're running in a 0 hertz span, so we're looking at this in time. The sweep time here is 1.6 microseconds, nothing special about that interval. And the detection likewise isn't terribly important. Here we're running a peak detector, but we could as easily use a sample detector. RMS though might not be a good choice because we want to be able to see the characteristics of short pulse interference if in fact a radar is behind this. So a peak detection scheme probably would be ideal. 1 megahertz also would be good in that it should give us a reasonably good response to the radar pulses, and again we could go to a wider bandwidth if we wanted to. Now, using one of the signal generators that I drew on the whiteboard, we're going to turn on the desired signal at 4 gigahertz, like so. And this happens to be basically a carrier wave type output. This isn't a true digital output, but this lab portion is just to demonstrate the phenomenon of RF front-end overload. So there's our desired signal. And as we look at this desired signal, we can go to a fairly short sweep time here. We'll take the sweep time down to 300 microseconds, 100 microseconds, 50. So far, we see no changes. Nothing's happening. Fine. So, and they can look at their output and say, nope, we're not getting interference right now. Our bit error rate is low, and so forth. Now, the next thing that we're going to do is tune this system down to 3 gigahertz, like so. Here, we're seeing just the noise in the quote receiver, unquote. And now we're going to turn on, as it were, the interfering signal. And here on the interfering signal, and I'll go to video triggering and bring this down, we see some kind of pulsed phenomenon occurring, and we'll go to a little longer sweep time. Here we're on a 5-second scale, and 1, 2, 3, 4, 5. So we have pulses that are occurring every millisecond coming out. These are fairly high power pulses that are coming out of an interference source. And this source could be something like, for example, a weather radar, which would be a terrestrial radar that's fixed, ground-based, or it could be an airborne system. In any event, we would actually not see this on all the time. We would see 10 or 20 of these pulses hit us in a row, and then we would see it drop out when the here, I'll go back to free run. We'd see it drop out when the radar beam isn't aimed at us, and then we would see the pulses occur when the beam does aim at us. But for the sake of tutorial clarity, I'm just going to leave this on and just let it run for what we're going to look at next. Suffice to say that if it's a real radar, you'll only catch this behavior occurring every 5 or 10 or 15 or 20 seconds. 5 seconds for a short-range radar, 10 for a long-range air search radar, 15 or 20 seconds or more if it is a weather radar. So here's the radar behavior down at its center frequency of, say, 3 gigahertz. And we have looked at this emission coming out of our signal generator. It's a very narrow band emission. So now we're going to go back up to 4 gigahertz, the frequency of our virtual Earth station. And now what do we see? Well, we see the desired signal, which again I'll turn off momentarily. There's our desired signal off with the pulses. Here's our desired signal on with the pulses. Oh, and look what's happening after each of the pulses. Let's go ahead and lock this down and take a little more careful look at what's happening here. We'll go to video triggering, like so. And we see that after each pulse occurs in time, a millisecond apart, and again, with a real radar system or other high-power transmitter, this would only occur momentarily every 5 or 10 or 20 seconds, we see this artifact occurring. And so let's zoom in on that in the time domain and see what we see happening here. And we'll go to a little delay on the triggering, like so that we can see what's happening here. Ah, very good. Now, bring this down. Look at that. That is the pulse coming out of the interference source, and this is the loss in response in the low noise amplifier after the pulse has ended, and this is the recovery of the amplifier back up to its full performance mode. So this system is losing all that data right in there. And depending upon the system, it can cause an effect that ranges, if it's an analog system, as I said, anywhere from speckles on a TV screen or a buzz if it's audio, to, if it's a digital system, an elevated bit error rate every time one of these pulses happens, to ultimately a problem with tiling or frame loss if it's something like a digital television broadcast service. And of course this would happen every 5 or 10 or 20 seconds when the radar comes around and looks at it. And if we see that happening, that's front-end overload right there. That's it. Case closed as far as that goes. But, and there is another way to look at this, and that's with a digital oscilloscope. For this we need, or any oscilloscope, for this we need to hook up an oscilloscope to the front end, and the scope itself needs to be getting an input from a discrete component detector, which is actually screwed onto the earth station auxiliary IF output or actual data output. Get this screwed on here. So what I'm doing right now is screwing the detector, which happens to be an Agilent or Hewlett-Packard 8474, but there are many commercial detectors that you can buy that would do this. And the detector output is going into the scope. And we'll get the scope running here, like so. Bingo. Now, what we see in the scope is basically the same kind of behavior as we saw with the spectrum analyzer, but we're seeing some additional details here. This is the signal from the desired source that the receiver is trying to look at, right here and right here. And this is the pulse from a high-powered source, which causes the low noise amplifier to overload. The low noise amplifier response right in here is actually dropping down like that. We just can't see it because it's being masked by the pulse activity. And then when the interference pulse turns off right here, we see the recovery of the amplifier coming back up to full performance. Again, if you see that happen, you're overloading the low noise amplifier. So it's really as simple as that. And what we've demonstrated here is what you'll actually see on a spectrum analyzer and an oscilloscope with a detector. And we've also demonstrated that you can use either a spectrum analyzer or a scope combined with a detector if you want to diagnose this at a receiver site. Now, the other nice thing about doing this is you can do this, of course, without having identified any candidate interferer whatsoever. Again, if you see that happening, you know it's front-end overload. If you haven't identified a candidate interference source yet, you can go out and look for it. You know it's not going to be a low-powered source in all likelihood. In the talk that I'll do next time, I will describe a pathological situation where you can see this occur even if you do have a bandpass filter on the front end of the receiver. But suffice to say that in normal situations, if you see this happening, the only possible solution is to put a filter on the front end of the receiver. There's no mitigation that can be undertaken with the transmitter short of literally turning the transmitter off. That concludes the whiteboard talk and the lab portion. Are there any questions?
We had a narrow interference that was continuous. How would you detect it if you were to see it? Just look for a drop in noise floor or something?
Good question, Randy. The question is, what if we had an interference source that was continuously present, that was not pulsed, where we couldn't see the recovery behavior occurring? Although I've never seen that happen, but I could imagine it happening if a broadcast source were somewhere in the area, what I would try to do, I know what I would do. I would disconnect the receiver's antenna from the rest of the system. I would look at the output of the low noise amplifier of that receiver and measure it and make a note of what it is. Then I would connect the antenna and see if that receiver's gain characteristic had dropped when I connected the antenna. Because if it drops when I connect the antenna, something's coming in from the outside world that's making it drop. And if it's a continuous source, we won't get to see this transition occur. We would see it depressed down there all the time, but we would have seen it come back up to that level when the receiver's antenna was disconnected. Yeah, that's a good question. I like solving problems like that. What would you do if? So, suppose. Anything else? Okay, well, thanks for coming to this week's talk, and next week we'll talk about zoo or pathological interference situations that don't necessarily diagnose themselves easily as co-channel or front-end overload. Thanks a lot.